The last component of topic 3 is to talk a little bit about gases and the kinetic theory or the kinetic model of ideal gases. And we'll start by talking a little bit about pressure. And when we're talking about pressure, we're talking about a force that's being relayed through a fluid. And we can talk about it in terms of liquids or gases, both of which you consider fluids. Here we're just going to primarily talk about it as it relates to gases. When we talk about pressure, we're talking about the force that's being exerted over a given area. And the units, if we look at the calculation, which is force over area, which is newtons over square meters, is actually then given a derived name, which is the Pascal. And so our units for pressure in the SI system are pascals. There are other ones that you'll see, particularly if you're talking about meteorology. Millimeters of mercury is one that you'll see occasionally, and also atmospheres. But for now, we're going to use pascals. And to give you kind of a reference for this amount of pressure, 1 atmosphere of pressure, which is the pressure at sea level, is about 1.013 times 10 to the 5th pascals, or we can also say 101.3 kilopascals. So a lot of times you're going to see your pressure measurements in kilopascals because that's a little bit more practical for a lot of situations. We can also use this when we're talking about the surface of a solid pushing against another solid, but primarily we use it when we're talking about fluids, those being our liquids and gases. And let's talk a little bit more, let's look at a little bit more at what actually causes pressure. And this is going to lead us into the discussion on the kinetic theory. We know that in fluids, in our liquids and our gases, the molecules have a lot more energy, so they're moving around. They have more kinetic energy, so they're moving around faster. When the fluid is contained, it's going to have some type of surface to actually contain it, whether it's the walls of a room or a container or a balloon or something like that. There's going to be something that's containing it. As those molecules are moving around, they're going to eventually be coming in contact with the inner surface of that container. When they come in contact with it, they're exerting a force on it, pushing it out. That force, you figure, is going to be multiplied by all of those molecules that are in that substance. So the more molecules you have, the more little collisions you're going to have, the more force there is. If the temperature increases, as we talked about before, when we increase the temperature, we're increasing the average kinetic energy of those molecules. And so now they're moving around faster. And so now two things are happening. Now not only are the molecules hitting the walls harder because they're traveling faster to begin with, but they're also hitting the walls more frequently because they're traveling much faster, so there's a smaller time period in between collisions. So more collisions per second, and they're hitting harder. And so this increases the net force on the inside of that particular container. And if the size of the container doesn't change, then by increasing the amount of force, if we refer back to our pressure equation, pressure is force divided by area. So if the area stays the same, the surface area of our container, but the force increases, then our pressure is going to increase. Now let's say that we have a container that's variable in size. So it has a piston in it, let's say, something like a syringe. And we push the piston in, we decrease the volume inside that container. And so by decreasing the volume inside the container, we're again causing the number of collisions per second to increase because there's more molecules inside a smaller area, and so they have to travel a smaller distance before they hit the walls again. And so there's more collisions per second. Now if we're going to apply that to our pressure equation, if the area is decreasing, so we're giving it a smaller area. We're pushing the piston in. That's decreasing the area. And as we can see clearly from our equation, if the area decreases, and in this case we just assume the force stays the same, already we see that pressure is going to increase. But when we're talking about pushing a piston in, what we're going to find is that the force actually doesn't stay the same. And the reason for this is that as you're pushing the piston in, you're doing work on the piston, which is then in turn doing work on the molecules in the container. When it does work on those molecules, it's transferring energy into those molecules. And in this case, it's being transferred in the form of kinetic energy. And so by pushing the piston in, you're actually increasing the kinetic energy of the gas molecules in the container. And if we increase the kinetic energy, what also increases? Right, the temperature increases. And so just by pushing that piston in, we're actually increasing the temperature. And so again, we're increasing the force, decreasing the area, and so the pressure inside the container remains constant. Now let's take a quick look at some examples of this. Okay, so here we have a little simulation with gas molecules, and we're going to pump this little air pump over here, and we're going to put a little bit of air in there. We're going to put some molecules in there. So you can see that the molecules in the simulation are moving completely random, and the pressure, again, you see the pressure kind of varies a little bit. It's not just even steady, and that's because there's actually not enough air molecules in there. If we give it a little bit more, it'll actually be a little bit steadier, but it still might vary a little bit. But within this given container, we have some number of molecules, and it's about 1 atmosphere here, so about 101.3 kilopascals. If we decrease the volume, so if we have our little guy here push the wall in, you should see two things happen. One, you notice that the temperature rose. The temperature rose about 82 Kelvin, and the pressure went from about 1 to about 1.5. So we increased the temperature, increased the average kinetic energy, and we increased the pressure. And if we decrease the volume a little bit more, you see that temperature rise up, and again there's our pressure increasing drastically. Let's do the opposite. Let's pull this out. As we're pulling this out, now the molecules are doing work on the piston, and so they're losing kinetic energy. The piston's taking that energy. We see our temperature decrease, we see our pressure decrease. Okay, so that's what happens when we change the volume. What if we add heat? Okay, so let's crank up the furnace, and now you can see our temperature rise up drastically and our pressure rises up drastically. So here our volume, our area is staying the same, but the kinetic energy is increasing. Let's take it down a little bit. And if we cool it off, the opposite happens. As we take away kinetic energy, the temperature drops, the pressure drops, and now we're back almost to about where we started. And if we do a combination of each, assuming we have a sealed container, at some point the pressure, the forces that are being exerted on the inside of the wall are going to become greater than what the actual container itself can handle. Okay, so there's just a quick look at how those three variables are interrelated. And in many cases, it's not just one or the other. If you have something like a balloon that has a variable surface, something that can stretch or compress, then you might have a change in temperature, pressure, and volume. So all three things are related. In that case, you start getting into our chemistry equation, PV equals nRT. And here we have pressure, volume, and temperature. And if you remember from chemistry, N is the number of moles, R is a constant value. And so for any sample of a gas, this PV over T is going to remain a constant that's equal to the number of moles times the ideal gas constant, R. And so if the temperature goes up, the pressure and or volume have to come down, and vice versa. Now this leads us to the kinetic theory of gases. And much as the name might imply, it relates to the movement of the molecules in a gas. And there are some basic assumptions that have to be made to apply the kinetic theory of gases. The first is that we have an enormous number of molecules. We can't talk about gases using the kinetic theory if we're talking about a dozen molecules or even 100 gas particles or molecules. We have to be talking about a very large number, and that those molecules move at a range of speeds. And remember, we've always talked about the temperature of a substance as a measure of the average kinetic energy. And if within a sample all of our gas is the exact same, so they all have the same mass, the only thing that's going to change the kinetic energies is the velocity. And so that tells us then that they must be moving at some range of speeds. Remember, we looked at the graph of molecule speeds when we talked about evaporation. And we also assume that the volume of the individual molecules is negligible compared to the volume of the gas itself. And so the molecules themselves are so small, especially when compared to the volume of the container that they're actually in. We also tend to ignore the collisions between molecules within the gas because they don't really have an effect. And we also assume that all collisions within the gases between the molecules themselves and the walls of the container are all elastic collisions. We'll talk more about collisions later on in the year, but an elastic collision is simply one where there's no loss of kinetic energy. We're also not going to worry about any type of intermolecular forces. We're going to assume that the only type of forces, the only time that forces are involved is when the molecules are actually in contact with either each other or the surface of the container. And that when these collisions occur, they take a very short period of time. And so that the time over which those collisions happen is very small compared to the time between collisions. And so a collision happens, it happens very quickly, the molecule rebounds off, and then there is a relatively long time before the next collision of that molecule. And then we also assume that all of these collisions, all of our molecules obey all of Newton's laws, all of those laws of mechanics that Newton developed. Now, it's really through these assumptions and understandings that we come to the idea that the average kinetic energy of the molecules is proportional to the absolute temperature. And we stated this when we talked about temperature scales and the Kelvin or absolute scale. There's a direct relationship between the Kelvin temperature or the absolute temperature and the kinetic energy. So if we double the Kelvin temperature, the kinetic energy of the molecules doubles. And if we're taking away energy, then eventually as we get closer and closer to 0 Kelvin, we're also getting closer and closer to 0 in terms of our kinetic energy of the molecules. And again, this is where that idea of absolute zero comes from. When an object is when the molecules of a substance are at absolute zero, they're going to have 0 kinetic energy. We can also use the kinetic theory to explain pressure and why pressure occurs. And so we have all these little gas molecules inside of a container moving around, and as they're moving around, they're going to eventually come in contact with this interior surface of the container, and they're going to hit it, they're going to exert a force on it. That force basically pushes the surface out, and as this happens over and over and over again, we have a continuous force pushing out. That's where pressure comes from. When you have something like a balloon, something that's flexible, the thing that actually determines the size is the point where that interior pressure is balanced with the exterior air pressure. And so if you were to blow up a balloon on, like, the ground, say, and you were to get into your car and drive to the top of a mountain, what you'd actually see is by the time you got to the top of the mountain, that balloon would have gotten larger in circumference to increase the volume so that it decreased the pressure. Now, when we have these gases in containers, one part of this is that those collisions between molecules in the container don't actually affect the pressure. And that makes sense because the pressure that we're looking at is what's being exerted on the surface of the container, and those collisions between the molecules don't have any impact on the surface. Again, as we've mentioned before, the faster they're moving, the more momentum they have, and when they collide, the greater the change in momentum, the greater the force. And so if there's more force, there's more pressure, and that increase in speed also decreases the time between collisions, so we have more collisions per unit time, again increasing the pressure. And similarly, a smaller container has less distance in between the interior surfaces, and so that also means less distance or less time between collisions, and so that's another increase in pressure.